And now it's time to get ready for our speaker, who is our very own Ben Glick.
Yeah, everybody, this is Ben, KN6UBF, and he's got a cool little project that he put together here, and yeah, I will let him take over from here.
Thank you. Thanks, Rob. Thanks, everyone, for coming. Give me one moment to share my screen. Nobody saw my password, did they? Oh, yeah, it's recorded. Slideshow. Okay, so the tongue-in-cheek title of this presentation is Toads HF, a digital layer cake that nobody ordered. But the real title is what I learned from building a digital mode from scratch with no research. So the no research part is going to come up a lot during this presentation. So just keep that in mind. Okay, so we're going to start by just going through where this project came from, talk about some similar projects that other people have done. We're going to go through in some level of detail how it works. I'm going to try and demo it live. You guys all know how live demos tend to go, so we'll just roll with that. Then I'm going to talk about how what's next for this project and where it's going and what I'd like to do. The main goal of this presentation is hopefully everyone in this room by the end of the presentation should at least feel like they kind of understand what's going on with digital modes a little bit. Like I said, if I can figure something out that kind of works with absolutely zero research, I think at least we can all understand, like in principle, how some of this stuff is working. And also, I hope we come out of this with a greater appreciation for every time you use WSJTX or like send someone a text that goes over the radio, a different kind of radio, but still radio. Yeah, so just try to demystify everything that's going on when we send digital text. Okay, so where did this project come from? So I'm an FT8, FT4 user occasionally. So I have WSJTX. I use it with this IC7300. I've made some reasonably fun contacts that way. I really didn't like how you have to sync externally. And by that, I mean, until I plugged in my GPS time source, I couldn't hear anybody. I found that sort of annoying. It just felt kind of inelegant that you have to use a separate clock a separate really very accurate clock in order to talk to people digitally. I also, I work in the tech industry. It's probably surprising to 0% of you that didn't know that. And I just wanted to learn more about how digital communication works in radio. And I'd heard of this thing called GGWave, which is, we're going to get into that in a minute. And I got this text from my friend, Brock, K06EZY. He just said, GGWave over amateur RF, ? And I thought, sure, sounds fun. So I figured I'll try it. That was in February of this year. And I tried it for a minute. It didn't go anywhere. And then it went to sleep for a couple months. And then Rob asked people if they had anything to share at these meetings. And I said, Rob, I might have a project for you. And then the last 2 months have been an insane amount of work to try and get this to work in time. So yeah, so I want to emphasize again, I did zero research. I did zero planning about what it takes to make a good digital mode. I just started trying stuff and saw how it worked. Okay, so I want to take a couple of detours here that sort of inform what I was thinking of when we were doing this. So many of you who are in this room, I'm sure, are familiar with these kinds of pictures. We call this the OSI model of networking. So the idea is basically that instead of every time we send data to anyone, we think about the voltage going from 0 to 1 and back to 0 and all of that. We build these abstractions. So we call things, so we call zeros and ones bits. We call groups of bits frames. We organize frames into packets and so on. And those are really useful because we get to operate at different layers of abstraction. And the same thing is true in digital modes. You don't always want to think about the modulation of what you're doing, or, you know, or am I doing frequency modulation or amplitude modulation, or what is, you know, how many microvolts am I receiving on my antenna and things like that. So we like to think at those higher levels of abstraction too. This mode is called Toad. We're going to get into that later, I think on the next slide. It's most concerned with layer 1, 2, and 6 of the OSI model, which is, we're mostly concerned with one would be things like when your RF carrier's on or off. Do you hear something coming out of the radio? These are physical things. You know, is my radio on fire? That's sort of layer 1. Layer 2 is going to be about data link. So that's like, how do I interpret what you're sending me? So I know I'm getting a voltage. What does that voltage mean? Those two are very important to us for Toad. And then we're going to actually jump all the way up to 6, which we call the presentation layer, which is how do I show this to the human person who's going to interact with it. Yeah, so that's sort of how I have the whole quote unquote ham US OSI model next to the OSI model here, but just know we're thinking about how do I get a voltage from my computer into here, over the air, and back to someone else who's ready to listen for it. I do want to address the name. So it's called Toad, which is short for text over audio digital, in parentheses, over sideband on HF. That is a backronym, so I came up with the name and then I came up with what it meant, which is why it's a little bit of a stretch. I had to put digital in parentheses there, and I also had to use one of the overs, but not both of the over. If you notice, there's like, that's why the O is lowercase. So it's text over audio, and then there's another over that's not there. So Toad is a family, actually, of protocols. Text over audio digital, that's Toad. And then there's the SHF is on sideband over HF. So you could just as well do Toad F VHF, like Toad over FM on VHF. I haven't tested that yet, but there's no reason it won't work. So I'll maybe if you hear something weird on N6NFI, it's that. I will identify, I promise. Okay, so now we're gonna sort of back up for a minute. Again, back to this whole, I didn't do any planning or research or anything. So in my high school English class, we learned about this thing called the hero's journey, or the monomyth, which is basically this idea that every story is actually the same story. They tend to go through a common sort of set of, like a circle, where you start somewhere, you want to do something, you get a call to adventure. So in this case, it was that text that we saw a picture of. I was called to adventure by my friend Brock. You refused the call. So that was me saying, oh, this is, sounds fun. It's never going to work. Then you meet some mentors. In my case, it was Connie, W6EFI, Mark, AD1M, and Gabriel, AJ6X. None of whom are here in the room. Connie is on Zoom. But they helped me a lot. We're going to get into what they did later. They help you get on the right path. They help you figure stuff out. Then you go out on the adventure. You go through what's called the ordeal. Why doesn't this thing work? I've tried everything. You get to a place called the abyss. I think we've all been to the abyss before, but that's where you think there's just no hope. So that for me was about 3.5 weeks ago. I was like, there's just no way this is ever going to work. Then eventually, if you keep persevering, you get your thing working, or you get your, you solve your adventure. and then you make it back to where you came from, but you're changed somewhat. So for me, it's I like FT8, and now I understand why there's an external clock, and I don't have a problem with it anymore. Yeah. So the reason I wanted to share this sort of story aspect is that I think like a lot of the time people who share projects and things, they focus on the like what I did and not on how the journey went, and how this is like a very non-linear process where you have good moments where you're really excited, you have moments where you're like, this is never ever going to work, and yeah. So it was a lot of fun to go through this process, and I think I learned a lot. Okay, so I mentioned GGWave. So GG is the creator's initials. It's Georgy Gurganov or something. I don't remember his actual name. But he made a protocol which is called GGWave. It's a text over audio or data over audio library. So he's a video production person, and he had a use for embedding into videos some metadata. So he would take a video, and then he wanted, when he was editing the video, he wanted to be able to say, I know where this came from. It was at this date on this time, wherever. So that has some really specific things where it has to be audible. There's a lot of like literal noise in videos that you're recording with a microphone. So it has to have be able to handle noise. And it has to work on normal frequencies that microphones record. There's also a pretty big community on Python, on the internet who use it through Python, through C, and some other programming languages. So there's a lot of like infrastructure out there that we can borrow. However, and this is where you really should do research before you start using something. It's really not designed for things where there's a bandwidth limit. So it uses roughly 6 kilohertz of bandwidth to encode text at, I think it's some absurdly small, it's like 30 baud or something. So that's double, for the record, that's double what's legal on HF. So you definitely can't do that. The reference decoder that's available in the open source community is extremely sensitive to noise in general, but especially fading. So fading from when you have a weak sideband signal, you get we've all heard on an HF radio, you hear the person coming in and out due to changing conditions in the air and stuff like that. So it's really, really sensitive to when the signal sort of comes in and out. It's definitely not suitable for AM-based modes, and it's really not tolerant of narrow frequency buckets. And the frequency bucket part I'm going to not talk about right now, but there's some slides in the future that'll make it clear what's going on there. So before we move on, I want to play. I hope this doesn't destroy all of our ears, but I want to play what GGWave sounds like. Okay, so yeah, it sounds a little like R2D2. It sounds sort of like a sci-fi thing. So what's happening here is this is it's the beginning, and then this is just A B C D E F G H I J K, all it's the whole alphabet. It sounds like this. Okay. Great. So I played that. Yeah, Shri, go ahead. This is the 6 kilohertz. Yeah, I didn't play this over the radio. This is just I used the encoder, I created a WAV file, and then that's all. Yeah, Daryl. Yeah. Yes. So I'm going to repeat the question for Zoom. Daryl said the beginning and the end of the GGWave tone. Yeah, so Daryl's question was, is that a preamble and a postamble? And the answer is yes. And if you don't know what a preamble and a postamble is, the preamble tells the decoder, start listening now. And the postamble says, I'm done talking now. So it's sort of like when you tell your phone, hi Siri, or you tell Alexa, hi Alexa. You can think of that like a preamble. Oh, Siri just woke up on my iPad. You're dismissed, Siri. Okay, so I had GGWave. I didn't know anything about it. I know a lot about it now. I studied its decoder and encoder in a lot of detail. I tried a bunch of stuff. So I tried to play GGWave as is into the radio. I wasn't able to to decode anything. The reason for that is because the radio actually has a filter that filters out anything illegal. Like it filters out at 3 kilohertz, which is good, right? Because it means I wasn't breaking any laws. That's very good. But it also meant I couldn't decode anything and I couldn't tell why. So that was like, there's, the only thing that's worse than having code that doesn't work and you don't know why is having code that does work and you don't know why. Yeah, and so I did a bunch of experiments with that. I have some pictures of those experiments that I'll show later. But I eventually decided, oh, this decoder must be crap, and I wrote my own decoder. And then I decided this, I still couldn't decode anything, and I decided this encoder must be crap. I need to have full control over it, and so I wrote my own encoder, and I started messing with stuff. And eventually, I was able to get it to decode off of my radio. So I would play it out of my computer into the radio and back onto the computer, sort of a loop back. I have a picture of that. I'll skip around. We'll do that. Yeah. So this is just when I played my own encoder of GGWave. So you can see what's going on here is it's consuming all the bandwidth from 0 to 3,000 hertz, 3 kilohertz, and it's actually consuming more than that. It's just getting filtered out by my radio. So what happens is on the 7300, this happens after it gets played by monitor to the monitor, but before it gets sent anywhere. So when I play it, I can decode it by ear, like it sounds just like it's coming out of my computer. But then if it goes out over the radio, it goes out like this with all the tones at the top filtered out. So that was incredibly confusing and frustrating for me. And I only figured this out when Connie, who lives 300 feet as the crow flies from me, so we're not subject to band conditions, we tried and we're like, I can hear you, like it's working perfectly. Why is my decoder not kicking in? And I eventually looked at this and sent an email to our email group, and Mark replied, you're consuming a lot of bandwidth there. Do you want to look into that? I said yes. So, but before we move on, what's going on here is the preamble looks like this. It's just a whole bunch of sound of lots of different frequencies. Then this is the message, where you see all these like lines and stuff here. And then this is the postamble. And another interesting thing you can see here is my noise floor. See how bright this area here is. That's the noise floor of my QTH, which is very high. I live in Palo Alto. I live in apartment complex with lots of people with switching mode power supplies and LEDs and all sorts of things that make my life miserable. Okay, let me move on back to so what Toad actually is. So Toad is a frequency shift keying mode, and what that means is I'm encoding digital characters as a whole bunch of sounds at different frequencies at the same time. So I call it FSK 16 choose 2. What that means is I have 16 buckets of tones. They go from 100 hertz to 900 hertz, and each bucket is 50 hertz wide. So to make a Toad signal, you take there's an alphabet, which I'll show you in a bit, but each character entry in the alphabet is basically 2 buckets. So it's 2 tones that are pure sine waves, so just like a specific tone at a specific frequency. You play them at the same time for a certain amount of time. We call that amount of time a frame. And then you play a certain number of frames, and that's a character. So in this picture, we have, this is like this letter, which is A, has the bucket at 200 hertz on and the bucket at 900 hertz on. So what you do is in your computer, you play a 200 hertz tone and a 900 hertz tone together for some amount of time, which in this case, we have 2 frames per character. And you'll see how those are defined later. But you play these 2 tones together for that amount of time, and that means A. And then the start and the stop, like the preamble and the postamble for me, are just all of the tones are on. So like I keep saying, I did zero research. I just tried something. This was the first thing I thought of. And it doesn't work that well. We're going to talk about why and what needs to change. But yeah, so that's sort of the general. Are we having a Zoom issue? Okay. So so that's how Toad works basically. Like when we keep playing stuff, think about that. That's what's going on. So I'll play a sample of Toad. Unfortunately, Toad sounds way less cool than GGWave. I haven't found a way to make Toad sound really good, but but here's what Toad sounds like. Yeah. Thank you. I appreciate it, but I think GGWave sounds way better. um, so let me see if what I've got here. Yeah. Okay. So this is I should have had this picture up. This is what happened when I tried to play the GGWave over my radio. So you can see on the monitor, which means when I turn up monitor on my radio, I can hear what I say. So when I play my own sound into it and I hear it back and then I decode it, it looks like this. You can see the noise. The noise filter. The noise here is filtering between, just 500 hertz and 3,000 or 3,500 hertz. It's 3 kilohertz wide because that's the only amount you're able to legally use. So why would the radio ever need more than that? But my signal is all the way up here. And you can see it goes above the noise because the monitor is not subject to the filter, which is, I know a lot more about the IC7300 than I ever thought I needed to. So what happens when you play it, this on the right-hand side was recorded by Connie at her QTH. You can see the Y scales are different. I'm sorry, that's my bad. But basically you can see there's nothing above the top of the noise, which means the whole top half of the signal was just filtered out by her radio. Or my radio. I think my radio. So yeah, so that's why the just naive GGWave over that's why that text. So it turns out that's a lie. You can't do that. but we tried anyway. Okay, yeah. So yeah, this is more of the same kind of stuff. This is a picture of what Toad looks like. So this is recorded on the computer, not recorded over a radio, which is why everything looks so clean. There's some harmonics, and it's kind of like ugly around the edges. That's because of my very, very bad digital signal processing that I did in a hurry. I have since made it better. But basically what's going on here, you can see these are all the tones on, and then this is, I think, K. Wait, no, this is Hello World. This is HELLO space WORLD. I can kind of read Toad by looking at the spectrogram at this point. That was not a goal of mine. Yeah, I'm not going to comment anymore on that. This, you can see again my noise floor here. That's kind of not that fun. The noise floor, the reason that I'm harping on this is you're going to see in a minute is the noise floor and the start frame or the preamble look shockingly similar. So telling the decoder when to decode when what you're hearing to tell what. Yeah, it's like if Siri was living in a house where everyone was just constantly saying "Hey Siri," and waking her up. Okay, so this is, yeah. So I went through all those experiments. I ended up coming up with this thing that I described. The key things about Toad are we have these 50 hertz wide bins. We have 16 bins. That fits in just under 1 kilohertz. The base tone is 100 hertz. It goes up to 900 hertz. So it's not so wide that it's crazy. It's like pretty reasonable. There's some good reasons to use that much bandwidth. There's some bad reasons to use that much bandwidth. I did it because it was the first thing I thought of. Yeah, so the key things are it's FSK, frequency shift keying, and there are 16 bins, there are 2 tones. That ends up meaning that we get up to 120 characters in our alphabet. I only need 45 for now. The alphabet looks like this. Oh yeah, one other thing to mention is instead of encoding the tones as a list of 100 hertz, 150 hertz, the tone bins, I sort of binarize. So each bin gets a 0 or a 1. You now have 16 zeros and 1s in a row. That's sort of a nice, easy way to represent things. So the alphabet looks like this. It's really small. I'm sorry. I forgot how big the screen here is. Isn't, yeah. So what you can see is you might be able to see that the bottom one is all ones. That's the preamble, postamble marker. And then every other one you'll notice has exactly 2 bits enabled. So there's 2 ones and everything else is zeros. And if you look really closely, oh, darn. I hope I didn't. Okay. Stand by. Thank you, Mr. Google. No, it was my browser that zoomed, not the Google window. I already did that. And by 200%. And then I wanted to zoom in though. Okay, so so sorry. For one thing that you'll notice about this is there's never a case where 2 ones are next to each other. And I did that because if 2 bins are next to each other, they're only separated by 50 hertz. So if you have any kind of drift in your signal where you're going to pick something up, it's very easy for one bit to bleed into the next, one bin to bleed into the next bin. So if you play a sound at 150 hertz and then it goes over the radio, it might come into the receiver sounding like 200 hertz. So to fix that problem, I just made it so that the alphabet didn't use any of the characters that have a 1-1 in them. Like I said, we have 120 characters, so that's for the combinatorics enthusiasts in the room. That's 16 choose 2 is 120. And I just subtracted 15, like 1 1 0 1 1 0 0 1 1 and so on. So we have 105 characters available. We only need 45. It's just uppercase letters, 0 through 9, and some punctuation. So hyphen, comma, period, exclamation mark, question mark, at, dollars. And that's it. So we have plenty of characters available. There's 45 in use today, the start and end. So I kind of use the terms preamble, postamble, and start frame delimiter, end frame delimiter interchangeably. That's all ones for now. Okay, what else do I have here? Okay, so the encoding process is something like this. This is going to sound really, if anyone here in the room is in signal processing for a living, I'm sorry. You're going to be very upset with me. So what we do is first we encode text to those toad symbols we were just looking at. Then the symbol is turned into a tone pattern with 2 sine waves in the audio domain. So in the frequency domain. So for those of you that do Fourier transforms, we do this in the place where it's easiest for me to write code, not in the place where it makes the most sense. So we encode everything into sine waves. Then we cosine smooth them. Critically, we cosine smooth them before we convert it to audio. This picture is actually from before I did that, which is why you see all these little artifacts at the edges. So this is kind of a cool picture because each of these is actually a frame. So you can actually see how long the frames are, not how long the characters are from this picture. And then once they're smooth, the idea of cosine smoothing, by the way, is we use a wavy line of cosine to make it so that instead of doing a hard transition from one character to the next character, it sort of gently, smoothly transitions. And that just makes the signal cleaner, basically. Yeah, yeah. It's actually a 2-key filter, or anyway. Yeah, so then we cosine smooth. Then I slap on the preamble and the postamble, which is just everything is ones. And then I convert to the audio domain to convert to the time domain to create the actual audio file. And then I just pass the whole thing through a 1 kilohertz bandpass filter because I couldn't be bothered to find a way to make it actually fit into 1 kilohertz with all these artifacts. So I just shove everything through a filter. Just works. There's some room for improvement in the DSP. Okay, decoding is sort of the opposite. We first take a Fourier transform. The Fourier transform lets us take a sound and extract the tones, the frequencies from it. So all these pictures that you've seen, like these are pictures. Oh, it's updating slow. These are pictures in the audio domain, the time domain. So this is 0 seconds. This is 7 seconds. So we play these sounds and taking the Fourier transform. Basically, you can think of that as like turning this graph sideways. So what it does is it just tells us, instead of telling us from 0 seconds to 7 seconds, it sounded like this. It tells us during this frame, there was this tone active and there was this tone active and everything else was 0. So I should have made a picture of that. I don't really know why I didn't, but think of it as turning the picture sideways. So we take the Fourier transform, we convert the signal to the frequencies, we find the 16 bins. We do that by pulling the base frequency out of the radio. So we assume if you found the SFD or the EFD correctly, you're on the right frequency. You find the bins, you detect the preamble and the postamble, you slice the message between the preamble and the postamble so you know when it started, you know when it ended. That means you divide by a known number of frames per second, and that's how you know how many frames there are and how many characters there are. You quantize or binarize, because there's only 2 options, to each bin to off or on. Just do a plain compare with that and the filter. Then we match that to whatever we find. There's a voting system. There's sort of a nearest fit system that we use. There's a mathematical operation. And then we handle redundancy. I'm going to explain that later. It needs its own slide. But that's basically how decoding works. Okay, yeah, so here's how redundancy works. So remember I said each character is n frames, and each character there's frame level redundancy and there's character level redundancy. What that means is each time you type a character, it sends n frames. That's configurable. When I do the demo, you're going to see what that looks like. And then there's an option to say send more than 1 character per character. So in this example, I've set that redundant characters, which is what it's called, to 2, which means if you type A, it's not going to send A, it's going to send AA over the radio. And then on the receive side, the receiver knows they're sending 2 of everything. And what they do is they vote. So in this case, we have 2 frames per character. We have 2 redundant characters. So the first thing that gets sent gets decoded this way as an A. The second thing that gets sent gets decoded as a B, because this tone bin has shifted. Like it should be here, but something went wrong with the ionosphere, a cosmic ray hit your radio or something like that. And it showed up over here. So the radio thinks that this frame is a part of a B, not part of an A. Then that's the end of this first character. The next character it gets both of them right, so they're A's. What the system does is it goes up and it says, I think you were an A, I think you were a B. It's going to record that as a tie, which produces this. I don't know what the character was. It was either an A or a B. Then the next character was definitely an A. And then because the characters are double redundant, we have basically 3 votes for A and 1 vote for B. And so the system says, A wins the election. I think this was an A. So again, those of you who do this stuff for a living are very upset right now. It's understandable. But and there are better. I have actually better plans in the short term that I will apply to this. This is a pretty naive way to do error correction, but it works. Oh yeah, and another thing that I found out by experiment was if you have more than 4 ways in the tie, just throw away the character. Because what was happening was with my super high noise floor, I was getting all these things that they would print out to me. Well, I got either an A, a B, a C, a D, an E, an F, or like all the way to Z, and I was like, this is useless. If it's so, if you think it's more than 4 things that all tied, just throw it away. It's not. It's probably not anything. Okay, so I already sort of got at this, but framing, which means deciding when something started and when something ended, is pretty hard. Right now, we do all ones. So everything is 1 to be the start, and everything is 1 to be the end. This is causing me huge bold and underlined problems. So what happens when I test with people who are, reasonably people over the radio, I can see the symbols. Like I have a debug mode in my terminal where I can dump all of the binarized zeros and ones, and I can look at them and I can say that's an A, that's a B, that's a Q. But my decoder never figures out that there's something there to listen to. So I can look at it by eye, or I can hear it by ear, and I can decode it. And I know the signal is coming through clean enough to decode, but the decoder never figures out that there's something there. And the reason is I assumed, this was a naive, not smart assumption, that RFI would add ones and RFI wouldn't take away ones. I figured that adding noise would, in the worst case, make me decode extra. But that's not what happened. What happened was, and I think I understand why, I think what happens is you get extra noise somewhere, and then the automatic gain control lowers the volume of the real signal, and then you get it to turn into zeros. And most of these radios, including this one, I cannot turn off all the automatic gain control. There is no way to do it. It's just not exposed. So, so that was fun to find out. And so reducing the threshold helps. So if you just say, instead of expecting 16 ones, expect 12 ones, expect 10 ones. That works, but then you have this problem where you can't see that. You have this problem where you're listening and no one's saying anything, but your decoder thinks somebody's saying 4T, D or E or Q, period, or 1, D or E or Q, period. Just starts decoding crap out of the air, which is not great. Yeah, Daryl, go ahead. Hmm. No, Rob, I'll repeat it. Yeah. So Daryl's comment was, but if you do the same thing with PSK31, you have the same kinds of problems. And you hear stuff even if there's nobody saying anything, which is, I believe, but this is really bad. This is happening like constantly. So I think one thing I could do better is instead of just blasting all ones, well, there's one problem with that, which is that when you set everything on high and you play all the energy, I think I end up overdriving the audio circuit on both sides, which causes a problem. The other thing I think I do is I think it'd be better if I played a known sequence. So I learned that this is what WSJTX, FT4, and FT8 do. They have this external clock, which I was complaining about and now love. But the other thing they do is the clock. So you're supposed to send with a very precise clock, but even that is subject to drift and conditions and the speed of light and all sorts of things. So what they do is within that, they play a known sequence of, I think, 7 things, and FT8 and FT4 only have 1 tone, and it's just it's like FSK 1. Yeah, it's like FSK1, I think, technically. So there's one tone and they shift it by a little bit, 50 hertz wide. And they use that known sequence to sync. The reason that they're so successful is that they only listen to 3 specific seconds. And it's very easy, if you know which 3 seconds your start frame is in, it's very easy to find it. The problem with my mode is it's totally asynchronous. The start frame could come at any time. So I think I'm going to improve it by doing either like some kind of oscillating pattern, like half ones, half zeros, then switch. So something that lets me actually sync rather than just all ones, and also doesn't have the AGC problem. Yeah, I get 3 questions.
And your start and stop frames are the same.
Yeah, and my start and stop frames are the same.
You have a lot of problems.
Yeah.
What was the other question? Oh, Shri.
Yeah, actually about this time sync, don't be hard on yourself at all. FT8, FT4, and all of the WSJT, they do sync 2 different reasons, 2 different ways. One is where they do the 1 second clock that you need to set. That's sheer coming out of simplicity or laziness, depending on what you want to call it. That need not be there. The other thing that you're referring to is the Costas array that they insert in, right? But you can have your own Costas array in there that you can recover, and then you don't need to have any time sync at all. So
yeah, that will be my plan, basically, to do that. I think Daryl had a question. And by the way, thank you to Gabriel AJ6X, who was on the phone with me for like 2 hours going through all of this stuff. I really appreciate it. I don't know. I think he's in SoCal today, but maybe when he watches the recording.
I think Shri already made a comment. It's basically a magic marker where you know it's a demarcation. You listen for that. If you miss it, you just don't decode the rest.
Yeah. Yeah, and that was my problem, was I could hear it. My radio could decode the characters, but it just never knew to start trying because it missed the start frame. And then, in debug mode, I can see it all, but I have to like look at it with my eyes, which is I don't want to do if it's a digital mode.
The other trick there is if your preamble includes some intention of how long the entire sequence is.
Yeah.
FT8 and FT4 did away with this by just having a known length. But most of the others, if the preamble includes a known length and the end occurs at the correct point, then you know you got it. And
right. You can just stop listening.
Exactly. And if it doesn't, if you hear an end somewhere else, then you know that you probably heard garbage.
As long as my end and my start are different.
I do want to say,
like I said, this is the first thing I thought of.
I do work in digital signal processing, and I've done far worse things and been paid for them. So don't be hard on yourself.
Thank you, Justin. I appreciate it. Okay, so I think I'm most of the way through here. I do want to try and demo this live-ish. We're going into a dummy load. Thank you, Elliot. So no problems there. Before that, this is a particularly good example of a signal I sent from Toad recently. So you've got the noise floor here, which looks super bright. You have a start frame. I got K and 6 UBF. This is the end frame, which looks just like the start frame, and then back to noise. The reason there's no noise here is that my radio stops listening when it's sending. So it just turns off. That my noise floor never looks that good. I just always be transmitting, and then I'll never have a bad noise floor. But I also won't hear anything. That's that. Yeah. I don't know, but it looks like 0. So Justin said in Discord, I'm gonna get the T-shirt made of this or something. He said a dummy load isn't it's something like a dummy load isn't not an antenna. It's just the worst antenna we know how to make. So thank you for that, Justin. All right, let's try and fire this thing up. So you guys can see this code. Basically, to set up Toad, you download the code. Let me zoom in. I see people squinting. What? The code for Toad. You download the code. You could get it from Git. Eventually, when it's ready, I'll push it to somewhere that's nice to install. It's not ready for that yet. You tell it what kind of radio you're using. So I've got IC7300 here. You can use any radio that someone has written a class for. I'll just show you that real quick because why not? So this is my IC7300 class. Connie contributed an FTDX10 class. I wrote a K3S class using the club's radio to test it, so thank you for letting me borrow that. This is Python. And Mark wrote a class for the true SDX. So that little tiny thing, you know, those are pretty cool. But anyway, so it's pretty modular. All you have to do is you tell it what kind of radio you're using. You tell it the radio audio configuration. So there's an in and an out. You tell it what port to use to control the radio. There's a tool I have called list towed devices, which tells you how to set that. So you can't see that at all. Okay, maybe we can see that now. So yeah, so you do list towed devices. You find the one that looks like it might be a radio. So in this case, the audios are USB audio codec. It's really generic. The reason is that they have a commercial codec that they have on here that they didn't bother like changing the name of in the configuration. Same here. The radio shows up as on Macs. It shows up as on Linux as dev TTY USB 0, which I don't know why it sounds like a radio, but I guess it is. And on Mac, it shows up as Silicon Labs USB to UART bridge, because they didn't tell Silicon Labs, I want you to customize the name in this version of the chip that you're selling me. So the USB to UART converter, yes, but the USB serial, like they could have made in their firmware where they power up the device, they could have sent a custom name over. Yeah, okay, true. That's all true. But anyway, it's not the best user experience. That's all I was trying to say. Then Rob, could you switch, or Alan, could you switch the camera? This button, P. Yeah, hold it. Hold it. Okay. No, it looks good. Oh, you can't. You shouldn't. Oh, don't share the screen. Just switch the camera to 3. And then, okay, yeah, make that a little bigger. So like drag this thing. Yeah. Yeah, perfect. Okay, so you can see the radio here, and you can see my screen, hopefully. Yeah. So I'm going to run Toad terminal, and it's going to ask me what frequency I want to use. It's a digital mode, so I'm going to use 14050. This is going to click a few times. You saw this change to 14050. It also changed to upper sideband digital mode, which is kind of cool. You can see it says I'm listening on IC7300. The port is dev this Silicon Labs driver. The audio in is USB audio codec. The audio out is USB audio codec. And it has this big inviting terminal that says send, which wants you to send something. So let's send CQ Toad. I'll play this. So I think I have my monitor on at 50. That's going to be fine. Crank that up. I'm not going to put the mic here because it's going to make horrible noises. So we'll play CQ Toad. If we're lucky, it'll decode. It didn't. That's awesome. Oh, it did. Okay, so it decoded off its own monitor. You get to see the error correction in action, which is great. You get CQ. This is either an O or a T. Then this is either an A or an O. Then this is either an A or a D. I really don't like seeing that many ties, but it's kind of readable, sort of. Oh, the next one worked better. It just lost the space. Yeah, so the way it works is just like this. You send, and then if you receive anything, it just pops up and says receive. Yeah, so that's how Toad works. I guess any questions? Yeah, Dave, go ahead. KN6UBF. It's playing. The volume is off. Is it okay? There we go. It decoded cleanly. Okay. Yeah.
Hang on a second. So Zoom can hear you.
Oh, thanks, Rob.
Yeah, I saw it. You picked 100 hertz as the lowest. How come you didn't push it up like 1K to 2K?
Because I didn't want to shift it. I didn't want to. So I need to play it close to the frequency that the radio is tuned to. I didn't want to have it. Basically, I didn't want to in software have to shift it back to the place I expected it. So and 100 hertz works well enough. Like it doesn't cause enough of a problem in audio that like if I was trying to use maybe 10 hertz or 20 hertz, it wouldn't work so well. Because it'd be too low and then the audio system would have trouble receiving it. But at 100 hertz, it works well enough. So basically the answer is my own laziness. All right. Yes, Soren, go ahead.
Yeah, I'm over here. My question is about identifying your transmission, because even if you type KN6UBF, nobody knows what that tone means.
Yeah, so that's a good point. So when I test this, I also have, of course, in my macro pad here, which of course you get worse at using the radio if people are watching you. So I also have my call by CW. I sometimes use a straight key. So I've been identifying with CW, basically, is the answer.
One comment to that. If you were trying to do this all before today, with money or whoever, that was not legal. But at this moment, it has become legal because you have documented it.
That's technically not true. It was legal before because I pushed the README to GitHub. So I actually thought about that. I genuinely wrote a README saying, this is FSK 16, choose 2. The bins go from the frequency to this frequency. The start frame is like this. The end frame is like this. So I had plausible deniability of saying this was legal because I published the spec. It's a very bad spec. Thank you.
Hey, Alan, does anybody on chat have a question?
Oh, I have a couple more slides.
I'm sorry.
All right.
Sorry.
We're getting ahead of you here.
Yeah.
Everybody on Zoom, hang on a second.
Andy on the 9am TalkNet this morning said he couldn't figure out what my spec meant. I'm sorry. I know it was not a very good spec. I promise I will write a better spec in the future, the near future. Okay, so I want to show a couple more things. So this bottom one, oh, Alan, you can make my screen bigger. You can turn off the camera. Yeah, we're done with that. Cool. So this is the cleanest I've ever received someone else's signal call sign. This is W6EFI. It's perfect. Usually it's not perfect. Usually it's W?E?FI or who knows what. Yeah, here's a W?EFI. Basically, you can see. Oh, I really should have made all these pictures bigger. You can see this is sort of like abstract art we have here. I think this is just what it's like to try something when it's really new. I think this happens. Yeah, so that's a moderate success. This is a really clean. So this is Connie saying, no, this is me saying W6EFI KN6UBF. This is as received by Connie. You can see it really clean. You can almost decode this. Well, you can decode this by eye if you know what you're looking at. So this is, just don't look at that. That was an issue with my encoder. This is W6EFI. Space is really obvious because they're almost touching. I decided if you want any two, like I was okay with the worst character being a space because you can usually still read stuff if there's no spaces. Space, KN6UBF, and then the end. So that was received over the actual air. I can see everything is decodable. It's been really, really helpful to have Connie. I think Connie has spent 4+ hours on the phone with me doing this. So we'll call each other and I'll say, do you have some time to do Toad? We'll sit down at the computer. We'll be like, why doesn't this work? Well, if we're lucky, we get and then you want headphone Realtek audio. Okay. Okay, we should be back now. Could someone maybe confirm?
Yep.
Someone on
Hear you
QS,
now.
are we here? Okay, great.
Okay,
QSL.
and just to let Zoom know, our internet over here timed out, so you didn't miss anything, and we'll just continue.
Yeah, well, you missed my very bad stand-up. Okay, so assuming we can fix this start and stop issue, which I think, like I said, Gabriel gave me some good ideas. Some of you in the room have given me good ideas. So thank you. Some of the unique / nice features of Toad are it's asynchronous, so you don't have to bring your USB GPS dongle when you go on a POTA activation. It's decodable by ear or eye if you're looking at your spectrum scope, which I think is fun. And it's got a flexible payload length. I think I do want to encode the length in the preamble, but it still will be flexible. It will just be flexible to maybe like 3 digits of 3 binary decimal digits, something like that. Theoretically, we could push high symbol rates. So I would love to be able to do this at 30 baud, which is high. I had to explain DSL to an intern a few days ago. That was fun. Just like the concept of waiting overnight to download a movie or song. Couple of pictures. Yeah, so flexible payload length, you could push a high symbol rate of maybe 30 baud with FEC, forward error correction. So like a better way of doing error correction, I'd like to go even higher. Today, it's only been tested at 8 baud. So that's a whopping 48 bits per second. Super fast there. Yeah, so today it's been tested on 10 and 20 meters. That's just because that's what my antenna works good on. I want to test 2 meters. So like I said, if anyone wants to decode Toad with me on N6NFI, let me know. Yeah. It would work on AM. I just haven't tested it. I've only tested it on sideband. Oh, well, this is a digital mode, right? So am I allowed to do digital at 6 kilohertz on AM? I don't know if yeah, Rick is shaking his head. Yeah, yeah. I think there's a legal issue there. But it's okay. Okay, letter of the law, maybe. Spirit of the law, absolutely not. Right? It's definitely digital. So I've been using 14050 through 14147 or whatever. You know, the digital section of the 20 meter band mostly. Yeah, yeah. Oh no, I'm saying for digital modes, you're only allowed to use 2800 hertz, right? After they changed they lowered this. There used to be that 300 baud strict limit, nothing above that. They replaced it with a 2800 hertz. Sorry, bandwidth limit. So yeah, so we can't do that. It should work with FM. I would like it to work to try it with FM. Here's what do I need? Okay, yeah. So this is like a summary of what we learned today. So assuming you have nothing but a computer and a radio, what do I need to make a digital mode work? We don't need that many things. So we need to agree on what an alphabet is and what sequences of zeros and ones turn into useful characters. That's layer 6 of that thing we were talking about. Well, it's layer 2 and 6 of what we're talking about. We need a way to encode it. For me, we're doing this 16 FSK choose 2 thing. We need some instructions on how to send it. That's like how many symbols do I send per second? What mode do I use? How do you decode the mode? How do you then go from the mode to the decoded mode to back to text? And then we need to frame. So my mode I learned is actually like it's a much worse version of Olivia, basically. If you're familiar with Olivia, we've got some picture stuff. Yeah, so it's a lot like in that it's asynchronous. There's a start frame and an end frame. It's a lot like Olivia in that way. Oh, and FSK, Olivia is also in FSK mode, although I think they're using many more tones, more active tones. Or you can use an external clock like FT8, FT4, all those good things. That usually has an extra sync. I didn't know that until recently. I thought we just trusted the clock perfectly. And then if you're lucky, you have extra bits like error correction, redundancy, you have checksums, and you have lots of patience and lots of time where you do something and it doesn't work and you don't understand why, and then you're really frustrated. That happens a lot. Yeah, apparently. So I learned some things. I learned a lot doing this project, obviously. The GGWave decoder is not good at noise, not good at dealing with any kind of noise. Synchronization is really hard. QRM can turn a 1 into a 0 just as well it can turn a 0 into a 1. That was really surprising to me. I figured adding noise would always add 1s. On the IC7300, this is fun. 0% power is really not 0 watts. It's like 5 or 8 watts or something. Yeah, so Connie, who lives 300 feet from me, was like, "Were you transmitting earlier?" And she called me once, and I'm like, "Yeah, I was. I don't think I was doing any damage. I had my radio set to 0 watts." And she's like, "No, I could decode you S9." So that's good to know. That's why I have a dummy load, even though I was on 0% power. Thank you, Elliot. And sometimes it's a good idea to try something without any planning that's sort of impractical or seems like it might be impractical, because you'll probably learn a lot. So there's some things I want to do next. I want to improve Toad. I want to fix the framing. That's step 1 or step 0. Then I want to use low density parity check codes for FEC. I was originally thinking of using Reed-Solomon encoding like GGWave does, but Gabriel said, don't do that. Low density parity check codes are much better. And he sent me a link to a book that I should read. So I will be doing that. I want to GPU accelerate my DSP steps. I was generating a bunch of signals, and when I walked away, I figured it'd take a minute. I walked back, it took an hour to run all these things. So definitely like running the code somewhere faster would be good. Better tone-to-tone transitions. So you saw all those artifacts. I want to clean those up. Better preamble. I already mentioned that a lot. And then once the reference system is working better, I'm going to write a spec and publish an actual spec that you can go download from the website and use it to implement your own decoder, your own things on top of my decoder, things like that. So that'll be fun. And then that's all the sort of Toad improvement stuff. And then I also want to do some Toad using. So it'd be really fun to test the higher baud rates. I'd love to do a Toad mode POTA activation. So I looked it up. Connie actually looked it up for me. There's no rules about what mode you use for POTA. So if we get 10 people in this room, or not in this room, to go do a POTA activation in Toad, then we could go get in the book, which would be kind of fun. It can be the same person on different bands. I didn't know that. Thank you. Daryl, go ahead.
Maybe an enhancement, but is I'm sorry, PSK31 and I think others use Huffman Common Code encoding to help maybe accelerate decoding. Have you thought about that?
No. Yes, I've thought about it.
Okay.
I haven't. It sounds like a lot of work to figure out.
Yeah. Okay.
But I've thought about it. It might be interesting to pursue. There's just like so many other things on the list. Yeah, and then I think it'd be fun to make a Toad repeater. Why not? Just one's listening, one's repeating. Other demo apps. Yeah, so Toad is a transport layer, in my opinion. So I built this terminal thing where you type things and it sends them and then it listens to receive. But you don't have to just use it for keyboard to keyboard. So you could use it for anything. You could send email over Toad. You could do packet, whatever you want. So doing other things that are not keyboard to keyboard. Okay, I'm sorry. I've went way over my own time budget and probably Rob's. So I think
when you're done, I think we still have some Zoom questions we haven't gotten to.
And Dave has a question.
Oh, let me get Dave in.
Yeah, thank you. So he said if I have it on many bands, going from one band to the other band, then it would be a hopping toad, which is a really good one. And I didn't think of that. So thank you, Dave. He'll be here all night. So finally, I want to say thank you to Connie, Mark, Connie W6EFI, Mark 81M, and Gabriel AJ6X. For all of their support. Like each one of them has spent several hours helping me with this. So I really appreciate that. Brock KO6EZY, that's a 0. That should be this should be an O. He sent me that text in February where he said GGWave over amateur RF ? And that's where this started. And then Rob for sort of making me finish the project by having me sign up for a date. I said I might have a project in mind, and he said, great, can you do it in June? And I said, no. I said, maybe July. And here we are. So finally, thank you for everything. This is the link. Oh, it didn't update yet. The link to where Toad lives is about to pop up. Oh, now I timed out. Okay, sorry, stand by. I'm just gonna switch to my cell phone. It'll be better. Okay, it's reconnecting. So the link is going to pop up along with a, let me share the screen again. The link is here along with a QR code you can scan if you're interested in learning more. You can email me at that email on the internet or my call. I'm on N6NFI all the time. You can find me. And I'm happy to answer any questions you have here. So thank you very much for your time and attention and interest.
Yeah. What we'll do here is, Alan, you want to read what's on the, let's clear the Zoom questions up real quick.
So it looks like we have one question from KE2CZX who left. Is there a maximum length for a message? How long do messages take to decode?
Yeah, so there's no maximum length. If I institute a pre-sending the length of the message, there probably would be, because I would probably want that that message to be like a fixed length number, so maybe 3 digits. So maybe it'd be 999 frames or 999 characters, because we never send just a frame. You always send an integer number of characters. So no, but maybe is the answer.
Anybody else in the room? Oh, Justin.
What were you doing that took hours to generate audio?
Oh, I was generating lots and lots of different. So this was in the abyss. Remember I talked about the abyss? When I was staring into the abyss and it was staring back into me, I thought maybe if I generated a bunch of, if I tried to encode and decode a bunch of things of interest out of the GGWave decoder or encoder and my own decoder. I was at that phase. I thought that it would be easier if I could plot everything that I could ever possibly want to send and look at the bits next to each other with the audio signal. So I was generating like thousands of, programmatically generating thousands of sequences that are maybe of interest.
If you would like to visit the abyss again, then I encourage you to go through the path of GPU accelerating this process. If you would like a practical solution, I would encourage you to look at your timings. And I assume you're passing back and forth to something like NumPy. There's really, really inefficient things you can do that will make seconds turn into hours. But if you enjoyed this, GPU acceleration is a great way to solve that problem.
I work at this large green company that you may have heard of, so I know a thing or two about GPUs. So I have some friends who can help me out with that. But yeah, sometimes it really does feel like staring into the abyss.
This might be just me, but
Uh-oh. I'm in trouble.
I know. Well, okay. Now, listening to the tones of the sample messages that you sent, I know you were talking about PAARA. I was thinking that if you ever went on PAARA or like did a contest-like situation, I would rat you out to the FCC for violating 97113A4 because it sounds like techno music to me.
Ah ha ha ha.
You know, I had a kind of a somewhere on the same line here was when you were doing the alphabet,
Yeah.
each tone is specific to the character.
Yeah.
So if you got really creative, you could actually create
Oh yeah, you
a
can
song
music.
or a jingle. Okay.
Oh, it's playing on my. It doesn't sound very harmonic to me.
So when you do this, you know, do POTA, it wouldn't be POTA, it'd be called TOTA.
That's a good one. Thank you.
Well, I was gonna say I heard that you can get warts from playing with toads.
You can also turn into a witch, right?
Yeah. Any other questions before this goes down to the gutter here?
It would be Toad F, like I think I said here. Yeah, it would be Toad F VHF, not Toad's HF. Toad's HF sounds way better.
All right. I think we're gonna move on, or Bob's gonna start salivating over there.
Yeah, this was a great presentation.
There's no doubt.
You learned a lot. I learned a lot through your experience that you shared. So this is really, really good. I have more questions that I actually want to ask you, but we'll do it over pizza or something because we don't have time. But we're a bit later than we usually are after our speaker. So if you